what is our atmosphere made up of today? And we can see that most of our atmosphere is just a few things. Nitrogen at 78%, oxygen at 21%. We had 99% of our atmosphere, two elements, all right? But we do have some other things. Argon is 0.9%. Now we're up to 99.9% of our atmosphere, which is three constituents. But we've been talking a bit about carbon dioxide here. CO2 today in our atmosphere comprises a very, very small number. We're looking at 0.04% of our atmosphere is carbon dioxide. When we go back to earlier days here when we were getting a great deal of outgassing, like I say, we know that number, that percentage was far, far higher. But now plants have taken the carbon dioxide out of the atmosphere, split the carbon off to produce other things, and return the oxygen out to our atmosphere. So, you look today, we're down to very, very little carbon dioxide, but look at that oxygen level, all right? So, what has happened? Let's just make an assumption. I'm gonna make an assumption that our carbon dioxide percentage was well over 90% back during this phase of our atmosphere. I got good reason to say that. We're going to take a look at our neighboring planets, and you're going to see some good evidence for that. But what the question I would have for you, where is all the carbon from the carbon dioxide gone? Where is it now?
Underground?
Why?
It's eroded.
No, you're right. He's absolutely right. Most of it is underground. Think about it. We had a lot of plant life back about 150 million years ago during the Pennsylvanian. A lot of these big trees died in a water environment, a swampy environment, subsequently covered by sediments, got deeper and deeper under the ground, heated up more and more, and turned into coal. A lot of our plant life in the United States and all around the world has turned into coal. It's underground, okay? Marine animals have turned into petroleum underground. Things like limestone, carbon in the limestone, a lot of that's from the carbon dioxide, underground. The vast majority of the carbon from the carbon dioxide in the atmosphere is under Earth's surface. That's where it's staying. What are humans doing today with all that carbon? We're digging it up and we're burning it, and we are returning carbon dioxide back into the atmosphere. Because when we burn coal or petroleum products, we're releasing carbon dioxide into the atmosphere. So we've seen, by the way, about a 30% increase in the amount of carbon dioxide in our atmosphere in the last 100 years. We've seen that's a significant increase in carbon dioxide, and most scientists will tell you it's because of what we're burning. We're digging it up, burning it, and returning it back to the atmosphere. Anyway, okay.
But at the same time, we are destroying forests.
Right, and well, we've got a lot of the carbon stored in forests as well. Yeah, so I mean, we're storing, the carbon dioxide isn't just underground. It's obviously in all the plants, so it's in the surface. Where a lot of other carbon dioxide is residing is in the soil. It turns out the soils hold a huge amount of carbon dioxide. The oceans hold carbon dioxide. Well, that's a whole other story, okay? All right, so there is our modern atmosphere. There's one other constituent I want to write up here, is water vapor. H2O, H2O gas. And I can't give you a percentage because it's variable. And that's we're just going to put here. It varies from place to place. Look at Arizona. We're very dry. I showed you that water vapor map earlier today. It's extremely dry here, whereas if we go down to the tropics or other places, there's a lot of it. But both carbon dioxide and H2O gas are very important because they're what we call greenhouse gases. What does that mean? It means those two gases, remember what I told you about the atmosphere, it warms from the bottom up. That long wave radiation that comes back up from Earth's surface gets absorbed by carbon dioxide and water vapor. All right? So if we're going to add more of those two things into their atmosphere, what's going to happen? It's going to get warmer. right? And that's the theory behind this global warming stuff you've heard about. That by adding this 30% increase of carbon dioxide to the atmosphere, we know carbon dioxide absorbs long-wave radiation. The atmosphere should be heating up. All right, water vapor does the same thing. Let's talk about atmospheric density. All right, so in other words, where are these molecules? Where do they reside? Those constituents, nitrogen, oxygen, all of that stuff, we can depict them as small little molecules here. All I'm trying to show you here is that the vast majority of these molecules are very close to Earth's surface. Why? Why are they close to our surface?
More pressure to the ground?
Gravity. It's the gravitational attraction of the planet Earth holds them close to the surface. So what we're trying to depict here is we get further and further from our surface, they get fewer and fewer. Therefore, our air pressure is going to get less. So let me show you the second slide here. Now, what we're showing you here is air pressure decreasing as we leave the surface. What you're seeing across the bottom here, start here, this would be ground level here at 0, is the air pressure. They're giving you air pressure in millibars. Now, that's one way we measure air pressure is in millibars. You guys remember what average air pressure is on the surface?
13.2.
No, yeah, okay. We're just going to go like this. We round it off to that. 1,013 millibars is the average surface pressure at 0 sea level. So we could put in 1,013. You can really, I don't mind if you just round it off to 1,000 average surface temperature when we look at a graphic like this. What this graphic is showing you is that as we increase in altitude, this is what our air pressure is doing. And so we've just put in the summit of Mount Everest here for comparative purposes. By the time we get to the summit of Mount Everest, which is just under 30,000 feet, we would have an air pressure of 300 millibars. What that tells you is that's about 1/3 of average sea level pressure. So what that tells you then is if you're climbing Mount Everest and you get to the summit, you're only breathing 1/3 the amount of oxygen that you would be breathing at sea level. And that's why most climbers that climb Mount Everest use supplemental oxygen the last few thousand feet. Now, a few climbers have made it to the summit without that. Most people need it. All right? But I think what this tells you is how quickly our atmospheric pressure declines. Sorry, Ruben?
Dead zone.
The dead zone, that's right. What is the dead zone? From about 25,000 feet up, it's called the dead zone because your body is slowly dying. All right? And so you can only spend so much time above 25,000 feet or you're dead. Ask how many people have died on Everest? A couple hundred? 400? All right. Then anyway, from 30,000 feet, it quickly diminishes to almost nothing as we continue up. So this is just a depiction of that. Most of our atmosphere is very close to the surface.